I'd like to welcome everyone to today's webinar. We'll be discussing what is big data. Before we begin, a bit about myself. My name is Tang. I've been in the IT industry for about 10 years, working in various roles from software developer and systems administrator to my current position as solutions architect at Rackspace Asia. My technical background is in the visualization cloud space, but big data has recently become a really strong interest area for me. Now, this webinar will be a first of a series of big data webinars we'll be running. The motivations behind this series really stems from the strong interest we see in big data from the wider industry. And through this series, we'll look to delve into several of the newer big data tools like Hadoop, MongoDB, and Cassandra. We will discuss what they are and how to use them. Today is about the what, though. What is big data? It's really important to set the scene of this series by discussing what big data is, since there is a huge amount of confusion and hype around the term. And we'll start by explaining big data by firstly talking about some use cases, followed by the what, the why, and the challenges of big data. Finally, we'll end today by giving a high-level overview of some of the well-known big data tools. Now, taking a step back, let's talk about three seemingly unrelated scenarios. House of Cards is an American political television series owned and produced by the streaming service Netflix. Last year, it won 9 Emmy Awards, and this year it's been nominated for 13, and it has regularly high viewership. By any accounts, this series is an absolute success. Now, as with any product or service, it's always difficult to guarantee whether something is going to be a success or not. But when Netflix bought the House of Cards back in 2011, the executives at Netflix knew with great certainty that it'll be a smash hit. See, the thing is, Netflix has a massive amount of data on how their customers interact with the service. They have data on each of the 30 million plays a day, including when viewers pause, rewind, and fast forward, when they watched it, and what device they watched it, as well as 4 million ratings and 3 million searches. This data means that Netflix has massive access to consumer sentiment in real time, something that no other film and television business has had before. So when the House of Cards series was looking for a backer, Netflix saw the same thing other production companies saw, an intersection of a successful lead actor, successful director, and successful television genre that could potentially make for a successful show. But they analyzed it further and used their data to verify that their customer sentiment would result in high viewership, thereby ensuring the success of the show and a reduction in the risk associated with their investment. Netflix further used their data to tailor certain elements of the show towards its customers. See the House of Cards cover on the slide? When designing this cover, Netflix analyzed the subscriber data to determine the average color of covers of successful shows of similar genres across a 216-degree color vector wheel to choose colors for the cover that would attract its viewers to the show. Now, Steve Jobs, considered as the father of the digital revolution, became the unfortunate victim of pancreatic cancer in 2011. In 2003, when he was diagnosed with cancer, Steve Jobs became one of the first people in the world to have his genome and his tumor's genome genetically sequenced. Sequencing the entire genome gave doctors an unprecedented amount of data and insight into the patient and their health state. And they're able to tailor and personalize the medication as the cancer mutated in hope to beat the cancer. Unfortunately, though, it didn't save his life, but it is known to have given him many extra years of life over a similar cancer sufferer, and has brought to the forefront the idea that genome sequencing at scale could play a key part in finding a cure for cancer. Now, most people know the story about how Target knew a teenage daughter was pregnant before her father. And if you don't, I can provide a link to the original article. However, what most people are unaware of is how Target knew this. Target, like many retailers, collects a huge amount of data on its customers. Information like what you've purchased, when you purchased it, how you purchased it, and so on. Hadoop also knows that if they can perform targeted advertising on mothers in their second trimesters of pregnancy, there's a high chance to capture that customer for the long term. But the question is, how do you find out if a mother is pregnant, particularly if the information isn't public knowledge? Target's data analytics teams tackled this exact question by analyzing its customer data, and they were able to identify 25 items that, when analyzed together, could give a strong accuracy around whether a mother was pregnant and even when she was expected to give birth. So to give you an example, if a 20-year-old woman bought cocoa butter lotion, a purse large enough to double as a diaper bag, and zinc and magnesium tablets in March, they could estimate there was about an 87% chance that she was pregnant, and the delivery date is sometime in late August. Now, it's through this method that Target could identify tens of thousands of expected mothers, including this teenage daughter. So how do these seemingly different examples relate together? Well, these examples in the area of retail, entertainment, and health really show the different ways that big data is being used to either give us a competitive advantage, reduce risk, or help us live longer and healthier lives. Big data is all about giving us detailed and comprehensive data-driven insights based on far more data than we've ever had or been able to analyze before, so we can make better data-driven decisions. And in order to play in the big data space, you need special talent and techniques, a lot of data, and special tools. Big data talent comes in the form of operations staff for the tools, and a key role known as the data scientist. The data scientist often has a background in computer science, statistics, analytics, and mathematics, and their role is to use the tools to analyze the data to discover trends. In many ways, they are the brains behind the big data operation. But one can argue that these skills and talents have been around for a long time. For example, in 1839, Matthew Maury of the U.S. Navy used big data techniques to create the first shipping lane system between Europe and America by collating tens of thousands of data points from hundreds of logbooks borrowed from captains of U.S. Navy and merchant ships. The data element of big data has also always been around since the beginning of time, but it's the advancement of the tools that have only now allowed much of that data to be collected and turned into the form that we expect. And that highlights the final piece of the puzzle behind why big data has only recently come to the forefront. The tools, the special hardware and software used to create, process, and store data had advanced far enough and become affordable enough to make big data economical. We can see this trend looking at the cost of computing power over the last 70 years. Where a computer with the processing power of an iPad 2 right now costs $100, in 1950 it would have cost 10 billion% more at $1 trillion. In a similar vein, the cost of storage has also dramatically decreased. In the 1980s, 1 gigabyte of storage would have cost about $1 million. Today, it sits closer to about 2 to 3 cents. And as a result of both these factors, we can now run several computers in parallel and store a lot of data, meaning we can now process faster and process more while still being affordable. Similarly, the affordability of computers also means we can find them everywhere, helping us collect that data. And it's these factors that has prompted the big data revolution. With the hardware becoming affordable, this in turn has prompted the development of software tools that help us store and analyze this data, allowing us to relatively easily reap the benefits of big data. And it's these software tools like Hadoop and MongoDB that will be the focus of this series. Now, we've discussed three key components of big data: talent, data, and tools. But there's one final ingredient that pulls these things together to make big data big data. and that is having the right mindset, or a big data mindset. This is critical because an organization may have all three components, but if the organization continues to use traditional small data techniques, then they'll never fully reap the benefits of big data. Schomburger and Cook here posited that there are three major mind shifts that need to be made to make for a big data mindset. The first of those shifts is that we must learn to utilize all data in our big data problems, regardless of its size, format, or complexity. Sampling, a process which involves selecting a subset of data to represent the entire data set, is a method we commonly use now, but was originally developed to overcome limitations around technology. Today, as we no longer are limited by this technology, we must adjust our thinking from small data sampling to the world of big data, where we analyze everything. The second of those shifts is that we must learn to embrace messiness of data as a trade-off for having vastly more data. Having accurate data is important, and in the past there was a heavy focus on data accuracy. But having a lot more data inevitably means that there's going to be more inaccuracy in individual data points. But as long as most of the data is accurate, we have the ability to establish trends we otherwise couldn't see. And it's these trends that are important to us, not the individual data points. Or thinking of it another way, sometimes 2 plus 2 equals 3.9, and that's good enough. The third and final shift is we need to change our discovery process to start with correlations. Where in the past we'd looked to think of the why or the causation first, before proceeding on to testing our hypothesis, big data allows us to find patterns or correlations first, and then work backwards to find the why. A clear benefit of this is it prevents wasted time proving incorrect hypothesis. The key takeaway from this, though, is that to get the most out of the talent, tools, and data, there's a need to change our thinking approach in the big data world. Now, the big data experts have noticed commonalities in big data problems, and I felt it was important to highlight these to you so you can recognize them as you further explore big data literature. The V's of big data, as it's known, describe 4 characteristics that are common among big data problems. The first V stands for volume and references the huge volume of data typical in a big data problem. The second V stands for variety and references the different data sources used in a single big data problem, which is often of different structure and complexity. The third V stands for velocity and references the rate at which data enters the organization, which is often very, very fast. And the final V stands for veracity and relates to the messiness of data, where some data is inaccurate, duplicated, or erroneous, and will need to be accounted for when solving the problems. Big data also has a number of challenges that often act as a barrier to its usage. For example, a change of mindset is often hard for us to make, especially when there is already sufficiently good system in place. Further, scale and talent challenges highlight the significant investment we must make towards big data. Scale references the software and hardware infrastructure needed for a big data environment, which can often number in the hundreds, if not thousands, of devices. And talent refers to the engineers and the data scientists that are required to successfully implement a big data environment, which can be both costly and extremely hard to find. But probably the biggest challenge to big data is not technical or associated with economics, but a social aspect. Big data gives us more insight into people's lives than we've ever had before. And being able to use this data to benefit us while preventing intrusion into a person's basic rights will likely be the hardest challenge to overcome for any organization. And as a result of these challenges, moving into the world of big data is often not led by any one single individual, but driven by the organization and the leadership. Now, having talked about big data to a great extent, let's begin to focus on the direction that these big data presentations will take. More specifically, though, we'll be looking at the software tools associated with big data. These software tools can be roughly categorized into 2 groups: data analytics tools, and high-scale transaction processing tools. Now, data analytics is the discovery and communication of meaningful patterns in data. When combining the power of big data with analytics, we can now look to process massive data sets, potentially from a number of different data sources, to find trends that are very specific and to which we can act upon. With small data analytics pose questions like, what is the most popular item sold in the month of October? Big data analytics poses questions like, what is the most popular item sold prior to a storm or hurricane in the central Midwest of the United States? Incidentally, Walmart posed this exact question to the analytics team to combine Walmart retail data with meteorological data, and they found among the normal items you expect to sell well, like batteries and bottled water, the sale of Pop-Tarts, the sugary breakfast treat, also increased prior to a major storm. Now, by stocking up on these prior to the storm and placing them at the front of the store, they were able to increase the sales of them quite significantly. And this highlights how much potential big data analytics has to organizations, particularly businesses. And the insights are only limited by the amount of data and data sources. Part of the reason why the buying and selling of data is expected to be one of the next big businesses. Now, there's a lot of big data tools that vary in their approach to performing analytics, and I'll show you 4 of the most common approaches here. Data warehouses are the most traditional and mature analytics tool that most people are aware of, and many have been reworked for big data scale. Data warehouses specialize in analyzing data sets that are of high quality and strict structure. MapReduce is a batch processing framework built for parallel computing. The concept behind MapReduce is the user will write 2 programs, a map and reduce program that sorts and filters data. The framework then takes these programs and coordinates the running of them across numerous nodes. Once each node has processed its data using the programs, the data is recombined to find a single consistent result. Probably the most well-known implementation of MapReduce is Hadoop MapReduce, one of the original projects of Hadoop. In-memory analytics targets the scenario of analyzing data in real time to facilitate efficient business decisions. When data warehouses and MapReduce excel at analyzing masses of data, they have drawbacks and they aren't designed to analyze this data in real time. As the price of memory plummets, in-memory analytics uses large amounts of memory to process data as it comes in, so results can be returned immediately. Last of the analytics approaches is the one that I find most interesting. Machine learning is a branch of artificial intelligence and looks to change the nature of the way we approach problems. Where in the past we explicitly told a computer how to do something, with machine learning we throw a ton of data at the computer and ask it to learn it itself. A good example of this is Google's self-driving car. Instead of explicitly telling it that it needs to go when the light turns green, Google simply throws a lot of data about driving at it, and the car learns that green means go. Now, machine learning forms the basis of many things we see on the internet today, like Google's search engine and Amazon's recommendation engine, and in many ways, machine learning is considered the future of data analytics. Now, big data analytics solve for the problem of analyzing huge amounts of data to find patterns. The other side of big data tools is the high-scale transaction processing tools, a set of tools commonly known to the industry as NoSQL. To understand why NoSQL tools exist, it's important to take a step back and talk about relational databases. The relational database model used by databases like MySQL and SQL Server was originally conceptualized back in the 1970s. It's a model that's designed to store data in the relationships. It does so by storing rows of data in 2-dimensional tables known as relations. Each row of data has a series of attributes describing it, and these attributes may or may not be enforced. For example, a person in the people table has 2 attributes, a name and a person ID, of which the person ID is enforced. Relations can also have relationships with each other, tying data together. For example, an activity has a person associated with it. Relational databases rely on the strict structure in order to operate effectively, and also rely on a language known as SQL to interact with it. Now, having existed for the past 44 years with very little change, relational databases have served us very well. But over the past 5 to 10 years, the IT landscape has changed dramatically. The Internet and Internet scale has demanded the need for greater speed, huge amounts of storage, and flexibility of storing data, key traits that relational databases were never optimized for. And this has made way for a new category of databases known as NoSQL or Not Only SQL. NoSQL databases are a group of databases, not a single type of database, that differ in the way that they operate to the relational model. And NoSQL database look to place a greater emphasis on certain characteristics that relational databases have been traditionally weak. Where the complex and highly structured nature of a relational database model can cause performance issues, NoSQL databases typically simplify the data model to improve performance by often stripping out features. An area where relational databases have also been weak has been in the area of scalability. Relational databases were created in a time when vertical scaling or adding additional resources like CPU, RAM, or disk to the computer was the best way to improve performance or add storage. Now, with computing being easily accessible and affordable, NoSQL databases are designed to horizontally scale or add additional machines to supplement load. A far better strategy where gains are almost always linear. And this is also why these tools fall into the category of big data, as they can often scale to many terabytes or petabytes. Additionally, the less structured nature of NoSQL databases makes for a far more flexible model. For example, if you want to do something as simple as add an additional attribute in a relational model, you'd need to modify the entire database schema. NoSQL databases, however, employ a model that allows you to flexibly add attributes and pretty much any other type of data to the database. This isn't to say, though, that NoSQL databases will replace the relational model. The maturity of relational databases in terms of talent, tools, and features is far more developed, but more significantly, relational databases can guarantee data consistency, whereas NoSQL databases typically don't. And consistency is important depending on scenario. For example, a bank will need to ensure data consistency so money isn't lost, whereas a common system on a website probably doesn't care. And this highlights an important aspect of both relational databases and NoSQL databases, that we should always use the right tool for the right job. As mentioned previously, NoSQL databases are not a type of database, but a group of databases that simply break away from the relational model. In fact, Carlo Strozzi, the person who coined the term NoSQL, actually refuted the name, saying that no-rel, or not only relational, was probably more appropriate. Here we show 4 common NoSQL models. The document database with common implementations like MongoDB and CouchDB breaks away from the traditional relational model by storing information about data in discrete units known as the document. Each document has a loose structure which can be modified or added to as required. In the example, we have 3 documents. One document details a brewery, and the other document represents 2 types of beer, Buds and Amstel, and their associated stock levels. The key value store, probably most well represented by Memcache and Redis, is one of the simplest data models, where each data entry is represented only by a key and a value. When we call a key, for example, first name, we receive the value, which will be bugs. The real value in a key value store is simplicity, and as a result, it's high performance and highly scalable model. Graph databases are based on graph theory and focus on relationships between elements. In a graph database, we can tie elements together based on related properties. So, for example, we can tie Alice and Bob together, since our data says they know each other. The use of graph databases, as you can imagine, ties itself quite well to social networks like Facebook and LinkedIn, where knowing relationships can add value to a service. Finally, columnar databases. Columnar databases are interesting as they've established themselves within the world of data analytics as opposed to the world of transactional processing. Like relational databases, columnar databases store data in tables. But unlike relational databases where data is structured in rows, columnar databases structure data in columns. This optimizes the database for data warehouse-like queries, where, for example, we want to find the average age of a customer or the most common last name. So today we've covered the what of big data, and I hope I've shed some light over a term that has a lot of hype in the industry, but still a lot of confusion. I've talked about some of the big data tools being used in the industry, tools I will focus future presentations on explaining and demoing. Big data is not one thing, but a mindset towards solving problems that leverages special people, technology, and of course, a lot of data. It brings with it numerous challenges, both technical, economic, and social, but also a huge amount of value. Value that on a micro scale could give us competitive advantage, but also on a macro scale has the potential to change the course of humanity by fundamentally changing the way we discover and learn. Big data is a subject area that people are only starting to scratch the surface on. And over the next few weeks and months, I hope to shed more light on the technology and tools around big data so you can begin to realize its value for organizations. So please do join me in my next webinar where we will focus on the tools that become synonymous with big data, and that is Hadoop. Thank you, and I'm happy to take any questions if you type them into the question box. So I have a question from William, which asks how we collect the data and where it comes from. The data can come from a number of different sources. It largely depends on the organization. So you can, for example, collect a lot of data from the internet. For example, Google naturally collects a lot of data from the internet as a whole. But if your organization focuses on certain areas that don't necessarily use just the internet, then you will collect it from that location. So, for example, UPS collects a lot of data from their delivery trucks. They have sensors on their delivery trucks that send them diagnostic data of the engines, and so that's where they collect the data from.